Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this. If you want to find the exact chemical recipe that created life on Earth, you actually cannot look on Earth.
Right, because Earth essentially ate the evidence.
Exactly. I mean, 4 billion years ago, the Earth was just, well, it was a mess.
A very violent mess.
Yeah. The Hadean Eon was this period of such extreme tectonic and volcanic violence that any prebiotic chemistry, the stuff delivered to our planet early on, it was subsequently subducted, melted, oxidized.
Or just eventually consumed by the very biology it helped create.
Right. So to find our own origin story, to really understand the raw abiotic synthesis of complex organics, we have to look somewhere else. We have to sift through the irradiated, pulverized dust of the moon.
Which is such a fascinating paradox if you think about it. The irony of planetary geology is that a biosphere is the ultimate destroyer of its own paleochemical record.
It cleans its own slate.
Exactly. The very processes that maintain habitability for you and me, like a dynamic lithosphere, a dense atmosphere, liquid water, a ravenous biological carbon cycle, those things ensure that the initial chemical inputs are just totally erased.
And the moon is the complete opposite of that.
Right. The moon is a geological graveyard. It lacks a global magnetic field, it has no atmospheric shielding, and its internal dynamo died billions of years ago. So it's basically a vacuum-sealed archive of the inner solar system's early bombardment history.
Which is exactly what makes the findings from the Chinese Academy of Sciences so pivotal. This was published in Science Advances on April 8, 2026.
Yeah, it's a massive breakthrough.
We're looking at an entirely new analytical framework regarding samples returned by the Chang'e-5 and Chang'e-6 missions. And they didn't just find trace carbon, right?
No, they found much more than that.
They systematically mapped multiple nitrogen-bearing organic species, specifically amides, that were synthesized directly on the surface of lunar soil grains. So we are seeing the physical proof of how exogenous organic matter evolves on an airless body.
Transitioning from raw cometary delivery to, well, highly complex structural chemistry. And the paradigm shift here really cannot be overstated.
It completely changes how we view these impacts, right?
Absolutely. The classical model of exogenous delivery treated asteroids and comets as just, passive carriers.
Like a delivery truck dropping off a package.
Exactly. The assumption was that a carbonaceous chondrite impacts a planetary body, scatters its polycyclic aromatic hydrocarbons or raw amino acids, and those molecules either survive the crash or they don't.
And if they land on a dead world like the moon, we just assume they sat there.
Right. The assumption was that they remain completely inert, maybe slowly degrading under ultraviolet radiation over millions of years. But this research totally dismantles that passive model.
It replaces it with something much more chaotic.
Yes, an active, violent, and continuous evolutionary pathway driven by the very forces we usually associate with complete destruction, hypervelocity impacts, and solar wind irradiation.
Wow. Okay, but before we get into the actual synthesis of these amides and the violence of it all, we really need to address the historical blind spot here.
The Apollo missions.
Yeah, exactly. I mean, the Apollo missions brought back hundreds of kilograms of lunar regolith in the late 60s and early 70s. And researchers did detect traces of carbon and nitrogen back then.
They did, but the consensus largely dismissed or marginalized those findings.
Right. So was that simply a limitation of Apollo-era gas chromatography and mass spectrometry? Or was it a fundamental misunderstanding of lunar surface chemistry?
Well, honestly, it was a combination of technological limitations and a massive amount of contamination paranoia.
Oh, sure. I mean, you bring a rock back from space, you assume any organic material on it is just from the lab.
Exactly. When you bring a sample back from the moon to a terrestrial laboratory, the immediate assumption, which is often the correct one, to be fair, is that any complex organic signature is just earthly contamination. Somebody breathed on it or the spacecraft outgassed.
Yeah. That makes sense.
The Apollo samples were handled meticulously, of course, but the analytical techniques of the 1970s required bulk analysis.
Meaning they had to look at a lot of dirt at once.
Right. They had to crush and dissolve relatively large amounts of regolith just to get a measurable signal. And when you perform bulk analysis, you entirely lose the spatial context.
You lose the morphology.
Yes. Carbon is in the vial, but you don't know exactly where that carbon was sitting on the individual grain of dust or how it was structurally bound to the surrounding silicates.
Okay, I like to think of Earth as an etch-a-sketch that gets shaken up every few million years by volcanoes and shifting plates, right? But the moon is like a dusty, locked diary sitting perfectly still in the solar system's attic.
That's a great way to put it.
But with the Apollo tech, it sounds like they knew the ink was on the paper of that diary, but they couldn't read the handwriting, let alone determine if the ink was printed there originally or if somebody just spilled a pen on it later.
If we connect this to the bigger picture, looking at the moon is essentially looking at Earth's lost baby pictures. But back then, the camera was just too blurry.
So how did Chang'e fix the blurry camera?
The Chang'e-5 and Chang'e-6 sample analyses bypass this historical bottleneck entirely by utilizing nanoscale in situ techniques.
Nanoscale, so we're talking incredibly small.
We are talking about transmission electron microscopy paired with nanoscale secondary ion mass spectrometry.
Wow.
This allows researchers to look at the exact morphology of the organics at the submicrometer scale without destroying the surrounding mineralogical context.
Wait, just to make sure we're all on the same page, a submicrometer scale that's less than a millionth of a meter.
Exactly. It's unfathomably small. And when they applied these highly spatial techniques, they realized the architecture of the organic matter was not uniform at all.
They categorized it into 3 forms, didn't they?
They did. They categorized the organics primarily into 3 distinct morphological forms: particle-like, inclusion-like, and surface-adhered.
Okay, particle-like and inclusion-like forms make intuitive sense to me. That's just discrete grains of carbonaceous material mixed into the dirt, or maybe trapped inside a tiny piece of impact melt glass.
Right, chunks of asteroid that got buried?
But the surface-adhered organics, where the complex molecules are physically bonded as a film or a coating onto the exterior of the inorganic lunar rocks, that points to some kind of secondary process, right? Because raw asteroid dust doesn't just spontaneously paint itself onto local basalt.
Oh, absolutely not. The surface-adhered morphology is the smoking gun for in situ chemical reorganization. It means the chemistry happened right there on the moon.
That's wild.
And if you look at the composition of these adhered materials, they are chemically dominated by carbon, nitrogen, and oxygen, but their structure is generally amorphous.
Meaning it's not a neat, orderly crystal.
Exactly. We aren't looking at highly ordered graphite or diamond, which you might expect from pure pressure transients, like something just getting squished really hard. We are looking at messy, complex, heterogeneous chemical matrices.
And nested within that messy, amorphous matrix is the really critical discovery, right? The amide functional groups.
Yes, the amides.
So just to break down the underlying chemistry for a second, amide features a carbonyl group, which is a carbon double bonded to an oxygen linked directly to a nitrogen atom.
That's the one.
And the implication of finding widespread amide bonds on the lunar surface is staggering, because that specific functional group is the literal backbone of peptide chemistry.
It is the exact structural linkage that joins amino acids together to form polypeptides and eventually proteins.
Wait, let me push back on this for a second, because terminology can be tricky here.
Sure, go ahead.
When you say organic matter on the moon, people immediately picture little green microbes or ancient fossilized space plants. How do we clearly separate biological organics from chemical organics so no one gets the wrong idea?
That is a very important distinction. In chemistry, organic simply means a molecule contains carbon, usually bonded to hydrogen, oxygen, or nitrogen. Doesn't mean it's alive or that it ever was alive.
Okay, so it's the raw material.
Right. What we are finding on the moon are abiotic organics molecules synthesized without biology. But finding these abiotic amates on an airless body forces us to completely reevaluate the thermodynamic hurdles of prebiotic chemistry.
Because making them usually requires a lot of help.
Exactly. Synthesizing an amide bond from raw carbon, nitrogen, and oxygen typically requires specific catalysts and significant energy inputs. In a terrestrial laboratory or in a theoretical warm little pond on early Earth, like Darwin talked about, we look for aqueous environments and thermal cycling to drive that dehydration synthesis.
You need water, you need heat, you need a cycle.
Right. And the moon offers literally none of those solvents. It's a bone-dry, freezing vacuum. Yet the chemical complexity is undeniably present on these grains.
Which introduces the primary physical contradiction of this entire discovery, doesn't it? If these complex amines require substantial energy to synthesize, but the moon lacks hydrothermal vents or liquid water or anything like that, the energy must be kinetic.
It has to be kinetic.
But when we look at the isotopic composition of these lunar organics, they're significantly lighter than the organics found in standard carbonaceous chondrites.
They are heavily depleted in the heavy isotopes of carbon and nitrogen.
So if these organics were just the surviving remnants of an asteroid impact, they should retain the isotopic baseline of their parent asteroid. The fact that they are lighter suggests a massive fractionation event, something sorted them.
And that isotopic fractionation is the mechanism that solves the thermodynamic contradiction.
How so?
Well, when a carbonaceous asteroid impacts the lunar surface, it is not a gentle, low-energy landing. It is a hypervelocity collision. We are talking about speeds often exceeding 20 kilometers per second.
20 kilometers a second. That is, I can't even fathom that speed.
It's immense, and the kinetic energy transfer upon impact generates shock pressures in the tens of gigapascals and localized temperatures of several thousand degrees Kelvin.
So it's basically throwing a fully built Lego castle, which is the original asteroid organic material, into an industrial blender. The asteroid, along with a significant volume of the target lunar regolith, instantly flashes into a superheated plasma and vapor plume.
Exactly. The original organic inventory of the impactor, those raw amino acids, the complex hydrocarbons, they're thermally obliterated. The chemical bonds are just ripped apart, reducing the organic matter to a chaotic gas of ionized carbon, nitrogen, oxygen, and hydrogen atoms.
The blender just obliterates the Lego castle into individual melted bricks.
Right. But as this vapor plume expands outward into the vacuum of the moon, it undergoes adiabatic cooling. The extreme temperature drop in that vacuum forces the vaporized elements to rapidly condense back into a solid state.
And this is where the kinetic theory of gases dictates the isotopic sorting, right?
Precisely.
In that rapidly expanding cooling plasma plume, the lighter isotopes like carbon-12 and nitrogen-14 have a higher thermal velocity than their heavier counterparts, like carbon-13 or nitrogen-15.
They move faster.
So they migrate outward faster and condense more readily onto the cooler surfaces of the surviving adjacent lunar soil grains.
Meanwhile, the heavier isotopes lag behind in the vapor phase. They either escape the moon's gravity well entirely due to the sheer violence of the expansion, or they condense later in different mineralogical sinks.
Oh, wow.
So what condenses onto the immediate regolith is a chemically novel, isotopically light film of highly reactive carbon, nitrogen, and oxygen.
It's an extreme distillation process. The impact shockwave acts as a catastrophic forge, destroying the original cometary organics, atomizing them, and then forcing those atoms to cross-link into entirely new amorphous structures as they rapidly quench onto the silicate surfaces.
The amides aren't survivors of the crash at all.
They are the direct chemical product of the explosion itself. That is unbelievable.
It perfectly explains the surface-adhered morphology we talked about earlier. The vaporized elements are literally vapor depositing onto the grains, chemically bonding with the oxygen in the silicates and the available nitrogen to form these complex functional groups.
So the violence of the impact actually provides the activation energy.
Yes, and the rapid vacuum quenching locks the new molecular structures into place before they can thermally degrade. It's a flash freeze of new chemistry.
Okay, so the impact physics cleanly explain the synthesis and the isotopic fractionation. But that immediately invites the ultimate counter-argument from literally any cosmochemist reviewing this data.
The contamination question again.
Exactly. You have microscopic grains of amorphous carbon containing amides analyzed in a state-of-the-art laboratory on Earth. Even with the isotopic fractionation pointing to a vapor plume, how do you definitively rule out that this fractionation or these specific amide structures aren't just the result of some highly specific modern terrestrial contamination?
Like maybe outgassing from the Chang'e spacecraft itself, or some artifact of the clean room handling.
Right. I mean, human beings are covered in carbon and nitrogen. How do they know it's not from us?
The researchers fully anticipated that contamination critique, which is exactly why the application of nanosims, again, that's nanoscale secondary ion mass spectrometry,
Right.
was so critical.
What did they do with it?
They didn't just measure the bulk isotopic ratio of the sample. They measured the isotopic ratio as a function of depth into the organic layer.
Wait, really?
Yes, they executed atomic scale depth profiling on these submicrometer grains.
Which is just an absurd feat of engineering.
Yeah.
Using a primary ion beam to ablate a submicrometer organic coating layer by atomic layer and capturing the secondary ions that are ejected to map the chemical gradient. It messes with your head to even think about that scale.
It's incredible, and what it allows you to do is essentially read the chronological history of the grain's exposure to the space environment.
Because the moon lacks a magnetosphere.
Exactly. Therefore, any material sitting on its surface is subjected to continuous, unabated bombardment by the solar wind.
And we are talking about a plasma of protons and electrons ejected by the sun, traveling at hundreds of kilometers per second, carrying energies in the kilo-electron-volt range.
That's a lot of energy, and when you expose an organic molecule to that level of ionizing radiation over geological time, it induces severe space weathering.
It physically damages the molecule.
Right. The incoming protons physically implant themselves into the carbon lattice. They induce bond cleavage. They physically knock out lighter atoms.
So what did the nanosims show?
When the researchers reviewed the nanosims depth profiles of these surface-adhered amides, they found dramatic variations in the hydrogen isotopic composition and a highly modified hydrogen-to-carbon ratio directly at the outermost atomic layers of the organics.
Oh, so the solar wind essentially sandblasted the surface of the molecules, creating a distinct weathering gradient that decreases as you move deeper into the organic film.
Precisely. The modification of the hydrogen-to-carbon ratio and the specific hydrogen isotope anomalies at the surface perfectly match the known physical effects of prolonged proton irradiation.
Which you simply cannot fake.
You cannot fake a million-year solar wind exposure profile in a terrestrial clean room. It's impossible. The depth profile acts as an undeniable, indelible fingerprint of authenticity.
It definitively proves that these specific organic structures sat on the lunar surface, fully exposed to the harsh radiation environment of the inner solar system for massive geological timescales.
Exactly. It completely rules out contamination.
Here's where it gets really interesting to me, though. If the solar wind is constantly blasting these grains with high-energy protons, is it just slowly destroying the organics, or is it actually part of the process that makes them more complex?
That is the perfect question, because the solar wind isn't just a passive authentication stamp. If we look at the interaction between high-energy protons and amorphous carbon matrices, the radiation is inducing further chemical modification.
But ionizing radiation is typically viewed as destructive, right?
Yeah.
I mean, it breaks chemical bonds, it strips away hydrogen.
In a biological system, yes, it's destructive. But in an amorphous solid, in the vacuum of space, it can also drive cross-linking.
Cross-linking.
That is the crucial secondary function of space weathering. The energy deposited by the solar wind protons can break a simple carbon-hydrogen bond, leaving a highly reactive free radical in the carbon matrix.
Okay, a free radical is basically an atom desperately looking for something to bond with.
Right. And if two adjacent radicals recombine, they form a new carbon-carbon bond, increasing the macromolecular complexity of the structure.
Oh, wow. So the radiation environment is simultaneously degrading the organics and driving them toward higher degrees of polymerization.
It's a continuous, dynamic equilibrium between destruction and synthesis. The solar wind is essentially baking these molecules into even more stable, complex forms.
So by piecing together the delivery, the violent impacts, and the solar wind, the research teams have unlocked a cohesive, step-by-step history of extraterrestrial chemistry.
They really have. Which brings us to the unified analytical framework proposed by this massive collaboration.
This was between the Institute of Geology and Geophysics of the Chinese Academy of Sciences, IGGCS, along with the University of New Mexico, and Changsha University of Science and Technology.
Yes. By integrating the morphological data from the electron microscopy, the isotopic fractionation from the impact thermodynamics, and the depth profiling of the space weathering, they've established a cohesive three-step evolutionary sequence for exogenous organics on airless bodies.
The three-step sequence. Let's break that down.
Step 1 is the exogenous delivery of raw primitive organics via carbonaceous chondrites and comets from the outer solar nebula.
The delivery truck dropping off the raw material.
Exactly. Step 2 is the impact-induced restructuring, where hypervelocity collisions vaporize the parent material, driving isotopic fractionation and vapor depositing entirely new, complex functional groups like our amides onto the local mineralogy.
The blender turning the Lego castle into a totally new structure.
Right. And step 3 is the long-term space weathering modification, where continuous solar wind irradiation implants hydrogen, drives cross-linking, and further matures the chemical architecture over millions of years.
This framework resolves the historical ambiguity of lunar organics entirely. We are no longer debating whether the carbon is contamination or just a pristine, untouched relic of the early solar system.
Because the evidence demonstrates it is neither.
Right. It is an actively evolved, highly processed chemical inventory native to the harsh constraints of the lunar environment.
And the implications of this extend far beyond the Earth-Moon system.
Well, yeah, so what does this all mean for the listener? I mean, beyond just knowing the moon has cool chemistry.
If this three-step process delivery, impact vaporization, and radiation-induced cross-linking can synthesize biologically relevant amides on the moon, it means this mechanism is ubiquitous across the cosmos. Everywhere. Every airless body in the solar system, from Mercury down to the asteroid belt to the icy moons of the gas giants, is subjected to this exact same combination of impact dynamics and ionizing radiation.
It fundamentally shifts the astrobiological baseline. I mean, we spent so much time modeling the origins of complex precursor chemistry in the context of habitable zones, looking for planetary bodies with thick atmospheres and liquid water.
Right, the classic search for life.
But this data proves that the vacuum of space, combined with extreme kinetic violence, is a highly efficient chemical forge all on its own.
The initial steps of chemical evolution, the leap from raw elemental carbon to the peptide-forming amides, do not require a planetary biosphere.
They don't even require an atmosphere.
No, they don't. It suggests that the inventory of complex organics available to early Earth was significantly more mature than previously modeled.
Oh, that makes so much sense. When the late heavy bombardment was peppering the Earth and the Moon billions of years ago, the material raining down wasn't just raw cometary dust.
Exactly. A significant portion of it was likely this highly processed, impact-synthesized, radiation-matured organic matter.
The Earth wasn't just receiving the raw ingredients for life. It was receiving the pre-assembled molecular scaffolding necessary for biology. It had a massive head start.
We've traced an incredible thermodynamic arc today. We started with the assumption that the moon was just a dead, static vault, preserving untouched cometary dust.
And instead, the analysis of the changing samples reveals the lunar surface as an active, multi-billion-year chemical refinery.
We've seen how hypervelocity impacts vaporized asteroids, fractionating isotopes in a cooling plasma plume to forge complex amides directly onto silicate grains.
And we've seen how the relentless bombardment of the solar wind etches an atomic history into those molecules, proving their extraterrestrial evolution while actively driving their complexity.
The combination of nanoscale mass spectrometry and rigorous impact modeling has finally allowed us to read the paleochemical record that Earth erased.
The diary is finally unlocked.
It confirms that the building blocks of life are not fragile anomalies requiring perfect planetary conditions to form, but are instead the inevitable byproducts of cosmic violence.
Which leaves us with a necessary recalibration of how we view the broader galaxy. I mean, think about it. If the lifeless, barren regolith of our own moon is quietly synthesizing the molecular zippers of biology under the brutal, unforgiving bombardment of space, what kind of wildly complex precursor chemistry is quietly churning away right now on the surfaces of countless other airless, irradiated rocks throughout our galaxy?
Just waiting for the chance to crash into a habitable world.
Exactly. We are surrounded by chemical incubators. Every time you look up at the moon, you aren't just looking at a dead rock, you're looking at the engine of chemistry itself.